Hi everybody, welcome to section 2.6, limits at infinity and horizontal asymptotes. So in this section we're going to take a look at what happens when we let x become arbitrarily large, either on the positive or negative side, and see what happens to y, or our function value f of x. We're going to look at the function described here, f of x equal x squared minus 1 over x squared plus 1, as x becomes large first. Remember, we call these rational functions. And if you look at the table of values here, that's correct to 6 decimal places, and the graph of f has been drawn on a computer here. So we take a look at y equal f of x, defined as x squared minus 1 over x squared plus 1, and look at that horizontal line y equal 1. And notice as x grows larger, you can see that the values of the function get closer and closer to 1. In fact, it seems like we can make the values as close to 1 as we like by taking x sufficiently large or sufficiently small, because it looks like the same on the left-hand side also. And we express this symbolically using our limit notation, and we would read this as the limit as x approaches infinity of our function x squared minus 1 over x squared plus 1 is equal to 1. In general, we use this notation. So we're looking at limits as x approaches infinity here. And we say that the limit of x as x approaches infinity of f of x is equal to L to indicate that the values of f of x approach L as x becomes bigger and bigger and bigger. And then here's our formal definition that we can state. So f can be a function defined on some interval from a to infinity. Then that limit as x goes to infinity of f of x equal L means that, once again, the values can be made arbitrarily close to L by taking x sufficiently large. Now, I don't think this is anything new for you, because you've seen this in AFT and pre-calculus before. They just call this end behavior, which is really what's happening as x gets arbitrarily large or arbitrarily small. In other words, on the two extreme ends of the function. Another equivalent notation for this would be just to say f of x approaches L as x approaches infinity. And I think this is the normal behavior, the normal notation that they use when they first introduce you to this idea in a pre-calculus, or in our case, those AFT courses. So this diagram below illustrates this definition, and we see as x gets really big as we look along our function here, we're approaching this line y equal L. And if we pick x sufficiently large, we can get as close to L as we want to here. That's really what our definition is saying here. And of course, we've called these horizontal asymptotes. And notice here is a couple different ways that some function or graph of f can approach a line L. Once again, which we call these horizontal asymptotes, as we look far to the right of each graph. On the right-hand side here, the function is kind of oscillating but dampening as it gets bigger, as x gets bigger and bigger and is approaching L. Where on the left here, it looks like it could be some type of perhaps inverse variation or a exponential decay function, where it's just smoothly approaching and getting closer and closer to that line y equal L. All right, now going back to that function that we looked back in figure 1, we can see that for numerically large negative values of x, f of x is close to 1 also. In other words, over on the left-hand side, this is also approaching the line y equal 1. So by letting x decrease through negative values without bound, we can make this, once again, as close to 1 as we like. So we also can say that the limit as x goes to negative infinity of this function, x squared minus 1 over x squared plus 1, is also equal to 1, since it's happening on both sides. So the general definition here on the left-hand side is saying that the function if the function is defined on some interval from negative infinity to a, then the limit as x approaches negative infinity of f of x is L. Once again, we can make it get as arbitrarily close to L by taking x sufficiently large negative, or in other words, making x smaller and smaller and smaller on the left-hand side. So, and once again, it doesn't necessarily have to get there the same way. Different functions can approach that L value on the left in different ways. Can come from the top, can come from the bottom, can oscillate back and forth and still approach that line y equal L. So, this gives us our formal definition of a horizontal asymptote. We can say that the line y equal L is called a horizontal asymptote of the curve y equal f of x if either one of these things happen. Either the limit as x approaches infinity of f of x is L, or the limit as x approaches negative infinity of f of x equal L. So if one of those things happen, we know that y equal L is a horizontal asymptote. Of course, they could both happen, and you'd have that where it approaches that line y equal L on both sides, but not necessarily, just one or the other to make that a horizontal asymptote. Okay, in our next example, we're going to take a look at hopefully a very familiar function to you, the function f of x equal 1 over x. And we're going to look at the limit as x approaches both infinity and negative infinity. Now, all we have to do for this is observe that when x is large, 1 over x is very small. For instance, as we get further and further along, making x bigger and bigger and bigger, those values become closer and closer to 0. And we're just looking at some powers of 10 here to make the numbers easier for ourselves. So you notice as we have x equal 100, where our value is 1 over 100, and if we had x equal 1,000,000, then we're at 1 over 1,000,000. So we're getting really, really close to 0. So in fact, once again, if we take x large enough, we can make 1 over x as close to 0 as we want. Therefore, according to that first definition that we talked about, that limit as x approaches infinity of 1 over x is 0. Now we can get similar results on the large negative side as we get further and further to the left or approach negative infinity. We can also show that function 1 over x also approaches 0. And then here's what that curve looks like. So we know that the limit as x approaches infinity of 1 over x is 0, and it's the same for as x approaches negative infinity for 1 over x. And of course, if you studied these curves, this one's called the equilateral hyperbola. In fact, this leads us to another theorem, and we can say that if r is greater than 0 and it's a rational number, then if we have functions in this family, f of x is 1 over x to the r, then the limit as x goes to positive infinity is 0 for these functions, and also as x goes to negative infinity. Of course, we have to realize that this x of r is defined for all of x. So now, our next example, we're going to take a limit, or a more complicated function, and look at its limit as it goes to infinity. And then we're just going to remind you of the properties that we're using as along each step of the way here, because, once again, we talked about this in class. If you're using the properties, you should indicate the properties that you're using them. So, as x becomes large, both the numerator and denominator also become large. So it's not obvious what happens to their ratio. We need to do a little bit of algebra first. Now, to evaluate the limit at infinity of any rational function, which this is, we first divide both the numerator and denominator by the highest power of x that occurs in the denominator. Now, we're assuming that x does not equal 0 since we're interested in only very large values of x. In other words, we're looking as x goes to infinity, so we don't have to worry about x being 0 here. So in this case, in the denominator, the highest power of x is an x squared. So we're going to divide everything in the numerator and denominator by x squared. And we're allowed to do that because when we're dividing by x squared over x squared, that's just like dividing by 1. So we get this limit that results when we divide by x squared. Then we simplify and split these up into 3 different terms in both the numerator and denominator. And we're still, again, we're using the limit as x approaches infinity. So this is just division here. Now, the book calls this limit law 5. Remember, this is our quotient rule. So we can split this up into the limit of the numerator divided by the limit of the denominator. Then once again the book is numbering these limits, but this is just splitting this limit up into 3 different limits in the numerator and denominator by the subtraction and addition rule. And also notice the 2 was taken out because it's a constant, so we said we can pull any constant out front. Then by direct substitution, for the limits of the constants, in other words, the limit as x goes to infinity of 3, and in the denominator of the limit of x goes to infinity of 5, that's just 3 and 5. And then notice when we're talking about as x gets really big in the other terms, all of those are going to 0 because they're either 1 over x and 1 over x squared. And we should be familiar with those graphs and realize that as x gets really big, not only does 1 over x, but 1 over x squared get really close to 0. That gives us our limit of 3/5. Now, a similar calculation can show us that it's the same on the left-hand side as x goes to negative infinity. Now, here's the graph of the function. We notice that that's our y-asymptote also, because it was the same on the left and the right, so both sides have that y-asymptote of y equal 0.6. Here's another example. Okay, in this next example, we're going to find the horizontal and vertical asymptotes of the graph of this function f of x, which is radical 2x squared plus 1 over 3x minus 5. Now, dividing both the numerator and denominator by x and using the properties of the limits, we've got the following. Now remember, we're dividing by x because that's the highest power of x in the denominator. And now remember, since radical x squared is equal to x for x bigger than 0, and since we're finding that limit as x goes to infinity, we can use the fact that radical x squared is just x, okay? So we end up with the limit of radical 2 plus 1 over x squared in the numerator and 3 minus 5 over x, okay? Now that gives us, using that quotient rule again, the limit as x goes to infinity of radical 2 plus 1 over x over limit as x goes to infinity of 3 minus 5 over x. Here we go with our properties again. We can take the limit inside of the radical. Remember, the radical is the same thing as a power of 1/2, so it works the same way as the power rule. And then we get the following limits. These should be pretty obvious. Just notice that the 5, we use the constant rule again by taking this 5 on the outside of the limit there. So that gives us radical 2 plus 0 over 3 minus 5 times 0, right? So that is radical 2 over 3. Therefore, the line y equal root 2 over 3 is a horizontal asymptote of that graph. Now, in computing the limit as x goes to negative infinity, we just have to remember that for x less than 0, when we have radical x squared, that's absolute value of x, which is the opposite of x, because once again, we're going x less than 0. So when we divide the numerator by x for x less than 0, we get 1 over x times radical 2x squared plus 1, which gives us negative 1 over radical x squared, radical 2x squared plus 1, which is the opposite of radical 2 plus 1 over x squared. So therefore that limit is the opposite of radical 2 plus 1 over x squared. And then once again dividing the denominator by x, we get 3 minus 5 over x again. Here comes those limit properties again and the constant rule. Notice we just took the limit underneath. 2 is a constant. We can bring that 5 in the denominator's numerator right here in this term and make it 5 here, right? And we end up with negative root 2 over 3. So that line y equal negative root 2 over 3 is also a horizontal asymptote. Now remember, the vertical asymptote is likely to occur when the denominator is 0, so that's when x equals 5/3. If x is close to 5/3 and x is greater than 5/3, then the denominator is close to 0. That means 3x minus 5 is positive. The numerator radical 2x squared plus 1 is always positive, so that means f of x is positive. Therefore, the limit as x approaches 5/3 from the right is going to give us positive infinity. Now, if f of x is close to 5/3 but x is less than 5/3, then 3x minus 5 is less than 0. So f of x is large negative. So we get the limit as x approaches 5/3 from the left, that root 2x squared plus 1 over 3x minus 5 is negative infinity. So on the left-hand side, it's going to negative infinity, but on the right-hand side, it's going to positive infinity. Therefore, here's what we're looking at. So notice on the left-hand side of 5/3, like we said, we're going to negative infinity. Over on the right-hand side, we're going to positive infinity. And then we have those two vertical asymptotes at positive and negative. I'm sorry, two horizontal asymptotes at positive and negative y equal radical 2 over 3. So that's limits at infinity. Okay, now let's take a quick minute here too and look at infinite limits at infinity. In other words, this notation, the limit as x goes to infinity of f of x equals infinity. Now remember, that's used to indicate that the values of f of x become large as x becomes large. And of course, similar meanings are used to say the limit as x goes to negative infinity could be f of x equals infinity, or they both could be negative infinity. Now remember, that does not mean these limits exist. It's just explaining the behavior of the graphs as x approaches positive or negative infinity. That f of x sometimes also goes to positive or negative infinity. But we are no way implying that these limits exist. So we're going to look at a familiar function, f of x equal x cubed, as x goes to infinity and negative infinity. Now, easy to see, when x becomes large, x cubed also gets large and becomes unbounded. In fact, we can make x cubed big as we like by taking x large as we want. So that means the limit as x goes to infinity of x cubed is infinity. Now remember, that does not mean the limit exists. We're talking about the behavior. We're just saying as x gets really, really big, x cubed, or f of x, also gets really, really big. Similarly, when x cubed gets really, really small or large negative values, if you want to look at it that way, it's going to negative infinity. So there's no limit, but we're just talking about the behavior of that graph there. And once again, you're familiar with the function, so you should be able to realize that on the graph itself. Thanks. That's it for 2.6. We'll talk tomorrow about this a little bit more and take a look at some problems relating to this. So If you need to, go back and watch, pause, take notes, whatever you need to do, but hopefully you can come to class tomorrow and take a look at some of these problems.